We've touched the integrals that had infinity in the limits, and now we want to deal with ones that have discontinuities or that become kind of unbounded as they approach some of the limits of integration. So one of the big things you'll deal with, this comes up a lot, is these kind of root functions here, and from 0 to 4. So if you were to graph a root function, like a 1 over square root of x, or even cube root of x, or whatever, as it goes to 0, as it's near 0, it becomes unbounded. It goes away. So those 1 over x to a power functions all kind of have that scoop, and they all shoot toward infinity near 0, and they all go to 0, but some of them go to 0 fast enough that this area is 0 and some of them don't. Anyway, so if I take a look at this, I say, okay, well, one of the easiest way to do this is don't even overthink it. Plug in the values here. So if I plug in 4 into this function, it's okay, it just gets me 1/2. If I plug in 0 here, it blows up, right? It's not defined there. So if it's not defined, either you have a really bad integral or you probably have an improper integral. And that's kind of an easy tell about what you're dealing with. So in that particular case, we just set this up as a limit. We say the limit as a approaches 0 of a to 4 or square root of x dx. Now, again, hopefully you're pretty comfortable with this integral by now. Maybe you're not, but hopefully you are. And that's going to be 2 square root of x is the antiderivative of the square root of x from, again, a to 4. So what we'll do is we'll plug in the limits of integration here. Once you get the limit as a goes to 0 of, when I plug in 4, square root of 4 is 2, and then minus 2 square root of a. Now I can take the limit. Now, obviously, when I take the limit here, that's going to vanish. So we get a convergent integral. And again, all it was it just had an area of 4. Now, for this one, for tangent function, we say, okay, well, is that defined? Well, if I plug in 0, tangent of 0 is 0 because it's sine over cosine. Sine over cosine. So I say, all right, is it sine of 0 is 0, cosine of 0 is 1. 0 over 1 is fine. That's just 0. It's not undefined. But at pi over 2, sine of pi over 2 is 1. Cosine of pi over 2 is 0. So I have 1 over 0. That's not defined. So that's pretty much, that's very clearly that territory of improper integrals. So what we have to do is we have to set this thing up as an improper integral. Say, okay, well, that's a bad point here. So this is the limit as b approaches pi over 2, 0 to b, tangent of x dx. Now, tangent of x is kind of, sure, I know what the antiderivative is here, but you may not remember yourself. So I'm going to walk you through how we get the antiderivative of tangent. What we do is we write this as sine over cosine. So then what we have to do is we have to take a u sub. We have to say, all right, well, I'm going to let u be cosine of x. du is negative sine of x dx. Now, we can actually swap the limits here. We can actually plug in for the new limits, and that would be okay. You could actually change what this limit is approaching and change that up there. And that's okay. In this particular case, I think it's a really bad idea. So what we're going to do is we're going to say the limit as b approaches pi over 2, where the x bounds are 0 and x bounds are b. The reason I want to say this is because now we're going to have negative 1 over u du. that's going to be our deal here. And we want to make sure that these limits, we're not confusing these limits for u limits. So obviously that is, the limit as b approaches pi over 2 of negative natural log of u from x equals 0 to x equals b. Then we have to plug back in. We get the limit as b approaches pi over 2 of negative natural log of cosine of x from, again, x equals 0, or so now we don't have to write the x, it's 0 to b. So that we can plug in limit as b approaches pi over 2 of negative natural log cosine b. And we actually don't have to put the 0 case, right? Because cosine of 0 is 1. Natural log of 1 is 0. So that term vanishes. We don't have to worry about it. We have this, negative natural log of cosine of b. If I take the limit, as b approaches pi over 2, well then cosine of b is going to approach 0. It's going to approach 0 from the positive side, which actually really doesn't even matter because we have an absolute value here. So what I'm really doing is the limit as, we'll just say y goes to 0 of natural log of y from the positive side. It comes from the positive side because we're doing the absolute value here, so I can just get rid of that. Now, if you know what the natural log looks like, the natural log looks like that. So the negative natural log just looks like that. So as we go to 0 from the positive side, this thing shoots off to infinity. Diverges. Shoot. Alright, well, too bad. Now what I like to do is I like to skip over to here because I want to make sure I have enough board space to deal with number 3. To deal with this, we already looked at this natural log function. We said, well, at 0, natural log is not defined. So that's our affinity point. Natural log of 1 is perfectly fine. That's equal to 0. So test your limit points, see if there's any issues. The antiderivative of the natural log x, we can use integration by parts. And if we did, we would get well, let's rewrite this first. This limit is a goes to 0 of a to 1 natural log of x dx, which is the limit as a goes to 0 of x natural log of x minus x from a to 1. So then I plug in 1 here, and this vanishes because natural log of 1 is 0. So I get the limit as a goes to 0 of negative 1 plus a, when I plug in a here, minus a natural log a. So then I have to say, all right, well, a goes to 0. Well, when a goes to 0, that clearly vanishes, right? That's not a problem. The problem is this, because when I plug in a, I get a 0 here. When I plug in natural log of a, I get a negative infinity. So I have a 0 times infinity. That's a L'Hopital's rule case. So what I actually have to write is negative 1 plus the limit as a goes to 0 of natural log of a all over negative 1 over a. Might ask yourself, why am I doing this? Well, again, I'm actually approaching from the positive side. I have to be careful. I don't really have to be careful, but we should do it that way to be safe. As this approaches 0, it goes to negative infinity. As this approaches 0, it's like going to 1 over 0, which is an infinity. So we need to use L'Hopital's rule. we get -1 plus the limit as a goes to 0 from the positive side of 1 over a over 1 over a squared. This just reduces to a, right? You multiply top and bottom by a squared. So that goes to 0. So our answer is actually -1. So this actually converges. This is really surprising to me. I did not expect this to converge. I don't know why I didn't expect it to converge, but I didn't. So I expected it to diverge. So then, learn something new every day, right? So finally, what I'd want to do is I want to talk about x to the p here. I want to say, all right, let's give us some time. Let's give us enough time to discuss this meaningfully. So we're going to have three cases. Again, we're going to have the case where x is less than 1, the case where x is equal to 1, or p, the case where p is less than 1, the case where p is equal to 1, and the case where p is greater than 1. But let's do the first case where p is equal to 1. So again, that's just 1 over x dx. And I'm shorthanding this. I'm not writing my limits out. And I'm doing that because I want to save that for the next piece. What you would do, you have to do is you have to say, all right, that limit is a as a goes to 0. Natural log of 1 is just 0, and then that would be the limit of natural log of a as a goes to 0. Well, as a goes to 0, natural log, as you go towards 0, it shoots down to negative infinity. So that is a divergent integral. So just like in the 1 to infinity case, the p equals 1 diverges. So that 1 over x, just straight 1 over x, is divergent. It's divergent whether or not you're going to infinity or whether or not you're going to 0. It's just not a very helpful case. Now, what we found before is that if p was greater than 1 for this, if this was 1 to infinity, if p was greater than 1, it would converge. And if p was less than or equal to 1, it would diverge. Let's take a look at the case where p is less than 1 here. But before we do that, actually, let's write out a general rule, right? So if it's not the case where p equals 1, we have sort of a standard antiderivative. We have that this is the limit is a goes to 0 from the positive side, a to 1, x to the negative p dx, which is the limit is a goes to 0 from the positive side of 1 over 1 minus p, x to the 1 minus p from a to 1. Now again, I want to keep going. When I want to plug in my limits here, when x is 1, 1 to a power is just, 1 to any power is just 1. So I have the limit as a goes to 0, 1 over 1 minus p, 1 minus a to the 1 minus p. So that's true whether or not p is less than 0 or p is greater than 0. But so let's consider the case where p is less than 0. I'm sorry, p is less than 1. I'm sorry. Let's consider the case where p is less than 1. Alright, so if p is less than 1, this limit, then what we know, if p is less than 1, 1 minus p is greater than 1. Sorry, it's greater than 0. Because if I, again, think about me subtracting p over here, it'd be 0 is less than 1 minus p. So 1 minus p is greater than 0. Why does that matter? That matters because this is a positive exponent. So now I have the limit as a goes to 0, 1 minus a to a positive exponent. Well, if it's just a positive exponent, then 0 to a positive exponent is just 0. 0 to a positive exponent is 0. Not a problem. So that's 1 over 1 minus p, right? Because this goes to 0. This is now 1 times 1 minus p. So what you find is that in this case, if p is less than 1, remember it diverged. It diverged in the infinite case, but it actually converges here. And we have one more case to go. P is greater than 1. So if p is greater than 1, one minus p is less than 0. Again, if I subtract over, I have 0 is greater than 1 minus p, which is the same thing. That's to say that. So now I can take the same limit, so now I have 1 over a to the absolute value of 1 minus p. Now, why did I do that? Well, if 1 minus p is negative, then 1 over... So if this is negative, then we can put it down here and it becomes positive, right? So what we do is we put this absolute value here to just tell anybody who's looking at it that no matter whatever you look at, this exponent is a positive exponent. So we're doing this conveniently because now if I go towards 0, I'm going towards 1 over 0. So I'm blowing it up. It's going to blow out to positive infinity. So I actually get positive infinity when I do this. So as a result, and the reason I get a positive infinity, you might ask, well, how? That's negative there. It should be negative infinity. It's because this is also a negative number. So those negatives cancel. And maybe you weren't asking that, but I'm telling you. So what we find is that it diverges. So basically what you're seeing is that for the finite interval at the 0, this x to the p, it always diverges. It doesn't matter if it's infinite or finite. That thing's going to diverge. But the behavior swaps depending on whether or not you're dealing with a finite or an infinite limit for particularly the x to the p case. Again, this is a really important thing. It's more important than it seems, and I'm hammering it because it's also one of the first times you're learning in mathematics to split things on this idea of a parameter, p. It's like, wait, why are we doing this? Why do we have this little p that we're tweaking? And the answer is, what we're trying to do is think about families, just like you thought about functions that had like shifts or stretches and stuff, and those were like scale values that you could kind of turn the dial on. Now we want to start thinking about functions that way. Okay, what happens if the function gets bent just like this? How does that change the behavior? You want to start playing with it. It's just an important piece of the mathematical journey to start messing with things and say, well, what if I change a value? Does that actually change the behavior or does it not? Where does it change? How does it change? What can I do to make it change? And so I'm trying to push you a little further than you maybe want to go right now, but as you look back, you're going to appreciate that sort of journey.